The next section, chapter 9, that we're going to look at here is solids and fluids. So take a look at a problem here in chapter 9. If we have a 1 cubic meter, of concrete, that concrete will weigh 5 times 10 to the 4th Newton. What's the height of the tallest cylindrical concrete pillar that will not collapse under its own weight? The compression strength of concrete, the maximum pressure that can be exerted on the base of the structure, is 1.7 times 10 to the 7th Pascal. So if we take a look at the little diagram here, we've got a pillar of some height. That's what we want to determine what the maximum would be. And then we have a downward force then of gravity equal to the weight of the pillar, 5 times 10 to the 4th Newton. So we're given the volume of 1 cubic meter for the concrete. We have the 5 times 10 to the 4th Newton for the weight of the pillar, and we have a compression that we're using to solve to of 1.7 times 10 to the 7th Pascal. So for this solution, the volume of concrete in a pillar of height h, unknown, and the cross-sectional area, which is given to us as the area, is equal to the volume, the volume is equal to the cross-sectional area times the height. Then we can find its weight, we can use the weight to solve for the height in this case. So we have the weight of the pillar is equal to the cross-sectional area times the height times the 5 times 10 to the 4th newtons per cubic meter. So in our relationships then, the force divided by the volume in this case will give us then a per unit volume amount. So 5 times 10 to the 4th newtons divided by 1 cubic meter then gives us a value of 5 times 10 to the 4th newtons per cubic meter. So we just divide it through by that value. So the next step then, we want to find out what is the maximum pressure then associated with this value. So the weight divided by the cross-sectional area, if we were to cut this up into a bunch of tiny slices and put it back together, then we would have a relationship that says that the weight is equal to the cross-sectional area times the height times that value that we just solved for here, 5 times 10 to the 4th newtons per cubic meter. And if we divide through by the cross-sectional area, of course they cancel. And now we have a value that, with the unknown value of h, times that 5 times 10 to the 4th newtons per cubic meter. So if the maximum acceptable pressure that was given to us in the problem is 1.7, that should be times 10 to the 7th Pascal, the maximum allowable height then is given to us by moving these values around. So the maximum pressure is equal to the height times that 5 times 10 to the 4th newtons per cubic meter. Moving the terms around, there's that maximum pressure, 1.7 times 10 to the 7th. Divide it through then by that 5 times 10 to the 4th newtons per cubic meters, and we see that the height can be no more than 3.4 times 10 squared meters. So that ends up being the maximum pressure for, or the maximum height for that given pressure of 1.7 times 10 to the 7th Pascal.